Hi and welcome. My name's Michael, and in this lesson we're going to talk about network addressing. So think about this for a second. If someone wants to send you a letter in the mail or even an email, they need to know your address. They need to know where to send it. Likewise, for something to be reachable on the network, it must be addressable. Let's get started. So I'm here in the interactive diagram, and I'm on the fourth section here on the left, addressing. And what we have here is an example of an IPv4 address, 192.168.1.101. Now, IPv4 is version 4 of the IP protocol, if you will. It is Internet Protocol version 4, IPv4. And it's been around since about the early 80s. Now, one of the limitations of IPv4 is that there is an upper limit of about 4.3 billion addresses in total. So let's look at the anatomy here. We have 4 numbers separated by a period. Each one of these groups is called an octet. So an IPv4 address is comprised of 4 8-bit sections called octets. The first octet is 192, the second is 168, the third is 1, and the fourth is 101. Each octet has a lower limit of 0 and an upper limit of 255, for a grand total of 256 values. And since each octet is an 8-bit section, 8 times 4 is 32, for a grand total of 32 bits in total length. So why do we call these octets? Well, if we look at one, we see it as an 8-bit binary number, so 8 octet. The minimum value of an 8-bit binary number is 0. The maximum value of an 8-bit binary number, and that's all ones, is going to be 255. So that is the basic anatomy of an IPv4 address. Let's look at an IPv6 address. This is the 6th version, or version 6 of the IP protocol. This has been around since about 1998, and it supports 340 trillion addresses. I will say the adoption of IPv6 has slowed somewhat. It was delayed due to network address translation, or NATing, and that permits mapping a private IP to a public IP. And really what we're seeing is a lot of the carrier networks like AT&T, Verizon, etc. are moving to IPv6, but enterprises are a little slower and somewhat behind. But the pressure is off due to NATing. And if we look at the address, it is a little longer than a regular IPv4 address. You're not going to be able to memorize something like this very easy. The one thing that we can do to make it look a little less long is everywhere there is a leading 0, so just like on our original example, 192.168.1.101, we could read this as 192.168.001.101. And it's the same with IPv6. We can actually compress these leading zeros. And if you have sections of leading zeros, those can all be compressed down and denoted by a double colon. So still not easy to remember, but a little less to write. Moving back to the address itself, we can see that it is comprised of 8 sections. Each section is a 16-bit field. Each digit is a hexadecimal. A hexadecimal is a base 16 number. That is 0 through 9, just like our decimal base, the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, 15, so on and so forth. However, it goes from 0 to F. And so if we look down here, we can see, the 0 starts at 0. And then when we get to 9, we're still at 9. But for the number 10, it is represented by an A. 11 is B, 12 is C, 13 is D, 14 is E, 15 is F, for a total of 16 values. And so if we look at this as a whole, and each hexadecimal number is a 4-bit number, we have a 128-bit address. Now, IPv6 addresses are somewhat unique. The first half is considered the network portion. The second half is considered the host portion and is often derived from the MAC address. What this means is that the first half of the address is the network address. This denotes what network this address belongs to. The back half denotes the host number or the host address within the network that is the front half. This is important to understand because subnetting IPv4 happens in the same manner. So if this host portion for an IPv6 is derived from the MAC address, what is the MAC address? The MAC address is a 48-bit number. It's also a hexadecimal, and it is the fingerprint of the network interface card. So if we look at the anatomy, we see it's a 48-bit number, and the first half is considered the OUI, or Organizationally Unique Identifier. This number denotes the manufacturer. So if this was a Cisco card, all Cisco cards would start with, B200E5. Now that doesn't mean that the MAC address can be changed, but that would be the difference between a universal or a local MAC address. A universal MAC address is one assigned by the manufacturer. A local MAC address is one that is created programmatically or manually. So if you're using a VM or something like that, it's going to create local MAC addresses. So the IPv4 and IPv6 addresses are the addresses on the network. The MAC address is the hardware address at the network interface card. It is the hardware fingerprint, if you will. So we have to have some way to map an IP address to a MAC address. And the way that we do this is through ARP. ARP stands for Address Resolution Protocol. So here we are back on our sample small network, the 192.168.1.0/24. This is our LAN, if you remember. And our computer down here has an IP address of 192.168.1.212. If it wants to communicate to IP address 192.168.1.101, it needs to know the physical address, the MAC address, to communicate to. Now, it wouldn't need to know that if the destination was outside of the local network. Then it would use the MAC address to get to the router. And so how does it get that address? It sends a broadcast request. And if you remember, a broadcast request goes to everything on the LAN. So it's going to send this broadcast request, and it's going to say, hey, who has 192.168.1.101? Tell me 192.168.1.212. Now the host with that target address, 192.168.1.212, is going to respond. It's going to say, hey, I have that IP, 192.168.1.101, and it's going to send this response back unicast. And if you remember unicast, that is 1 to 1. So the request goes out broadcast, the response comes back unicast for ARP. At this point, both of these devices are aware of one another's MAC addresses, and that information is stored in what's called the ARP table. In the next lesson, we're going to start talking about what this IP address and other examples look like in binary, so that we have some understanding as to how network masks are applied. And we need to know that so that we can see how we apply network masks when creating subnets. This lesson is now complete. Thanks for watching.